Hi, everyone. Welcome back to P2. We're a little more well lit than we were at the end of P1, but that's okay. Here in P2, we continue Chapter P and the basic rules of real numbers. And what we're going to do is talk more about exponents in this section. So we talked a little bit about exponents in P1 and how they would pertain to just, evaluating certain expressions, but we're going to look at some more rules for if we are dealing with multiple exponents across multiple expressions at the same time. So what we're going to do is introduce some rules, prove those rules with some very basic examples, do a whole bunch of simplification, and then apply it to the real world using scientific notation. All right, so let's go into some rules. So from P1, we have this nice slide of rules in P1, all rules that we remember, right? If we're doing x times x times x so many times, that would be x to the n. X squared would be x to the 2. X cubed would be x to the third. And everything after x cubed would be to the fourth, fifth, and so on. Any number raised to the 1 power is itself. Any number raised to the 0 power is 1, unless x equals 0, but we're not going to deal with that here. Negative things raised to exponents, we have to be careful. Don't forget that if it's a negative number raised to the nth power, we're doing that negative number n times. But if the negative's on the outside, the only thing being raised to the n power is the x. So you do x to the n first, and then you make it negative at the end. And of course, we can only distribute exponents in the case where everything is multiplied or divided on the inside, like a times b times c over x times y times z. But in the case where things are added or subtracted, we are not allowed to distribute exponents in that way. We're going to introduce one more new rule here, and that's going to be that so long as x doesn't equal 0, x to the negative n, so if we have an integer exponent, right, a negative exponent, not just a natural number, if we have x to the negative n, what we're allowed to do is say this is 1 over x to the n. So in a way, negative exponents drop down. If you have x to the negative n, then the equivalent would be 1 over x to the n. X to the negative 3 would be 1 over x cubed. And likewise, if we have a negative exponent in the denominator, we can also bring it back up. So there's this element of like negative exponents, they can flip between the numerator and denominator, and then they become positive. Okay, so introducing some more rules, we have the product rule. So if we have two exponential terms being multiplied together, x to the a times x to the b, we can simplify this as x to the a plus b. So two things with the same base multiplied together, we can add their exponents. And here's a little proof why. X to the fifth times x cubed, well, x to the fifth would be x times x times x times x times x. X cubed would be x times x times x. So if we drop those parentheses, we have 1, 2, 3, 4, 5, 6, 7, 8 x's. So that would be x to the eighth, which we could have also done by just saying this is x to the 5 plus 3. So a little bit of proof as to why. Similarly, for quotients, x to the a divided by x to the b, when we are dividing things with the same base but raised to different exponents, we can subtract them. So multiplied together, add exponents, divided, subtract exponents. X to the fifth over x cubed, well, x to the fifth is 5x's, x cubed is 3x's. And what we saw when we were doing fractions at the very tail end of P1, we saw we can cancel out x's. So here we can cancel out an x pair, cancel out another x pair, cancel out another x pair, and we're left with just a pair of x's in the numerator. Well, x times x would be x squared divided by 1 would be x squared, and we could have also found that by subtracting the exponents. If we have a power of a power, so we have x to some power, where the whole thing is then raised to another power, what we will do in this case is multiply those exponents. So notice that this is a little different from what we had before. X to the a times x to the b, we add those exponents, but x to the a to the b, we multiply. So please be careful to note the difference of those rules. As some proof, x cubed to the fourth, well, x cubed to the fourth says x cubed times x cubed times x cubed times x cubed 4 times. Well, each of those x cubes are sets of 3, so x cubed becomes x times x times x 4 times. We drop the parentheses, and you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 x's, x to the 12th, which is also the same as x to the 3 times 4. Power of a product, so a little bit more proof as to why we're allowed to distribute across multiplication. X to the n times y to the n times z to the n. So again, kind of the rule that we had in P1. And some proof, x times y to the 5th says x times y times x times y times x times y times x times y times x times y 5 times. Drop the parentheses. Let's regroup. Multiplication is commutative, so we're allowed to move x's and y's as freely as we want across multiplication. Let's put all the x's together, all the y's together. Let's regroup the x's and let's regroup the y's, and you see we have 5 x's and 5 y's. So x to the 5th times y to the 5th, which we could have done by just distributing that 5. So again, we had that rule in P1, but now we're proving it. And similarly for power of a quotient, same thing, we're allowed to distribute powers in such a case. But one new kind of rule would be x over y to the negative n. Well, this is going to combine that negative exponent rule we had before along with this one. So if we have x over y to the negative n, we can first start by flipping the inside to get rid of the negative, kind of like that x to the negative n, flip it to the denominator. That's kind of what we're doing here, just taking some liberty and jumping a few algebraic steps. And now from here, this is just like the previous one, y to the n over x to the n. So 3 over 2 to the 5th, we can distribute as 3 halves times 3 halves times 3 halves times 3 halves times 3 halves. Well, fraction multiplication, 3 to the 5th over 2 to the 5th. Well, we could have gotten via distributing that exponent. 3 over 2 to the negative 5th, we can use the rule that we have up here. It says flip the inside to get rid of the negative. So we now have positive 5 as the power, but we flip the inside from 3 halves to 2/3. And now we can distribute that 5, just like we did in the previous one. Okay, we also said that x to the 0 equals 1 in P1. We can prove that here. X to the a over x to the b, well, that's x to the a minus b. Well, this is a rule that we had. This is one of our first few rules. But if we make a and b the same power, well, x to the a over x to the a would be x to the a minus a. A minus a, any number minus itself, is 0. So x to the 0. But also, any number divided by itself is 1. So x to the a over x to the a equals x to the 0, right? X to the a over x to the a equals x to the 0, but x to the a over x to the a also equals 1. So a little bit of proof as to why x to the 0 equals 1. Now, let's do some simplification questions, right? Fun part isn't going over the rules. Fun part is doing the examples. So let's get right into it. Exponential expressions are fully simplified when all of the following conditions are met. Each base only appears once. So in some cases, we might have multiple x's, multiple y's, multiple z's, multiple 2's, multiple 5's, and so on. Our expression is fully simplified when every base only appears once. We don't want to have multiple x's if we can avoid it. Each exponent is a positive number. Typically, we don't like having negative exponents, so if we can avoid doing that just by flipping negative exponents between the numerator and denominator, that would be fantastic. And also, no power of a powers, or in other words, just as few parentheses as possible. So let's do 5 to the negative 4. Well, any number raised to a negative exponent is 1 over that thing raised to the positive power. So 5 to the negative 4 is the same as 1 over 5 to the 4th. Well, 5 to the 4th is 625. 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625. Okay. Negative 5 to the negative 4th. Okay. Again, anything raised to a negative exponent can be dropped down to the denominator. So let's drop negative 5 down to the denominator and make that exponent positive. And now negative 5 to the 4th, we talked about this in P1, negative numbers raised to even powers are positive. Negative 5 to the negative 3, okay, negative 5 to the negative 3 says let's take negative 5, drop it to the denominator and make that exponent positive. Well, negative 5 to the 3, negative numbers raised to odd powers are negative, so we get negative 1 over 125. You can also write 1 over negative 125. That is completely correct. It's just that when either the numerator or denominator is negative, it looks a little nicer to write that negative on the outside. But if you were to write 1 over negative 125, that is perfectly correct as well. Negative 5 to the negative 3. Be very careful. The only thing being raised to the negative exponent is the 5, right? Very different from here. This says negative 5 raised to the negative 3. This says 5 to the negative 3 and make it negative. So the only thing dropping down to the denominator is going to be the 5. So this becomes negative 1 over 5 to the positive 3. 5 to the 3 is 125. Okay, so again, from P1, please be very careful with negative exponents and negative stuff on the outside. So again, from P1, just be very careful when we don't have parentheses written for negative numbers. 2 to the negative 5th times 2 to the 9th. The rule that we have for two exponential terms being multiplied together is that we will add the exponents. So 2 to the negative 5th times 2 to the 9th says 2 to the negative 5 plus 9. Negative 5 plus 9 is 4. 2 to the 4th is 16. Simple as that. A little scary to begin with, not so scary when you add the exponents. 2 to the negative 5th times 2 squared. Same thing, we have two exponential terms being multiplied together, so we add the exponents. Negative 5 plus 2 is negative 3. Only difference from the previous question to now is that we have a negative exponent. That's okay, there's nothing wrong with that. All it says is we need to drop this down to the denominator, and 2 cubed is 8. Okay? 2 to the negative 5 squared. So again, note that this is a little different from what we had in the previous line. This says two exponential terms being multiplied together. This is one exponential term being raised to another power on its own. So here, multiplied together, we add here, power raised to a power, we multiply. Negative 5 times 2 is negative 10. If we have a negative exponent, drop it to the denominator and make it positive, and 2 to the 10th is 1024. Okay. 4 squared to the 3rd. Again, this is a power raised to another power. So 4 squared cubed says 4 to the 2 times 3. 2 times 3 is 6. 4 to the 6 is 4096. 6 to the 6th to the 1/3. Again, even though that this is a fraction, it doesn't change anything. If we have a power raised to another power, just like we did here, we are going to multiply. 6 times 1/3 would be 6 over 3. 6 over 3 is 2, and 6 squared is 36. 7 times 6 cubed. Again, be very careful. The placement of our parentheses tells us exactly what is being raised to the 3rd power. If we had no parentheses written, it would be the exact same. Remember that we always do exponents before multiplication. PEMDAS, P-E-M-D-A-S, exponents before multiplication division. So this says only raise 6 to the 3rd power, which is 216. And now we can multiply 1512. 3/4 to the negative 3. The rule that we have for fractions with negative exponents, technically what we can do is take the whole thing and do 1 over 3/4 to the 3rd. But to save us some work, what we can do is to get rid of the negative exponent, flip the inside first. Okay? Once we have flipped the inside, everything on the inside is multiplied or divided. So we are allowed to distribute our exponent. 4 cubed is 64. 3 cubed is 27. Again, key part here, negative exponent for fractions, flip it to begin with. It's a little bit easier to work with. 7 squared raised to the 14th, all over 7 to the 25th. Don't put this into your calculator. It is very, very big. So what we can instead do is say, well, this is a power raised to another power. In that case, we multiply. 2 times 14 is 28. Well, now we have a exponential term divided by another exponential term. So we can subtract the exponents. 28 minus 25 is 3. 7 cubed is 343. 5 to the negative 3 times 3 cubed over 5 to the negative 5 times 3 squared. Well, I haven't really mentioned it before because we haven't really needed to mention it before. But note that we can only combine and use all these rules when the bases are the same. So notice that we can't combine 5 to the negative 3 and 3 cubed because those bases aren't the same. Everything we've been doing so far has been when the bases have been the same, such as here, 7, same base, we're allowed to subtract exponents. Here, not the same base, we can't add. Here, not the same base, we can't add. But what we can do is group bases together. Notice that we have a 5 in the numerator and a 5 in the denominator, 3 in the numerator and 3 in the denominator. So why don't we group those pairs together? Okay, well, for just this first fraction, 5 to something divided by 5 to something, if terms are divided, we can subtract, and the same can be said for the 3's. So 5 to the negative 3 over 5 to the negative 5, we can subtract exponents. 3 to the 3 over 3 squared, we can again subtract the exponents. Negative 3 minus negative 5 is negative 3 plus 5. Negative 3 plus 5 is 2. 3 minus 2 is 1. 5 squared is 25. 3 to the 1 is 3, 75. So just be very careful doing these problems. You might also be wondering, why didn't we flip negative exponents? Why didn't we change this to bring 5 to the negative 5 back up and 5 to the negative 3 back down? And you are very welcome to do that. What you would get is 5 to the 5 over 5 cubed, and then you would just have 5 minus 3, which is 2, and that's where we got anyway. So what you'll notice in some of these is that there's not always one correct way to apply these rules. There's different rules you can use, right? We have a whole set of them. So just because you didn't use the rule that I did, if you got to the same answer, it's very difficult to come up with the correct answer using rules incorrectly. So if you wanted to instead change these negative exponents to positive ones by flipping each one, you're allowed to do that too. It takes a little bit more work, but just because you're being less efficient doesn't mean you're being wrong. Okay. 5 times 6 times 7 to the 10th over 5 times 6 times 7 to the 8th. Again, we have multiplication. If everything on the inside is multiplied or divided, we are allowed to distribute those exponents. But again, be very careful. The only thing being raised to the 8th power is 6 times 7. 5 does not get that 8 because 5 is on the outside of what is being raised to the 8th power. Okay, well, kind of like we did in the last question, notice that we have a pair of 5s, we have a pair of 6s, pair of 7s. So let's group those together. 5 to the 10 over 5, 5 to the 10 minus 1, 6 to the 10 over 6 to the 8, 6 to the 10 minus 8, 7 to the 10 over 7 to the 8, again, subtract. Do those subtractions. Yeah, these are really large numbers. I don't know who came up with them. That's okay. What is this? 3,445,312,500. Naturally, you guys all could have done that in your head, right? Well, let's start doing these things with variables instead. It's very nice and concrete when we can do these with numbers, but the whole study of algebra is that we want to introduce x's into these types of things. So just because we have x as a base, it doesn't change how we do anything. All it means is we're going to leave an exponent answer in the end. So x to the negative 4 raised to the negative 15. Don't forget this is multiplication, right? Power raised to another power. We multiply. Negative 4 times negative 15 is positive 60. So instead of being able to evaluate at the very end like we were for the other problems, the last set of problems, all it is we just leave our answer as x to the 60th. And this is a lot prettier than what we started with. Okay. 2x to the 5th times 17x to the 12th. Kind of like we were pairing things off earlier, what we're also going to do is pair off coefficients and pair off variables. So notice we have 2 times 17 and x to the 5th times x to the 12th. So let's group our constants together. We'll group our x's together. 2 times 17 is 34. X to the 5th times x to the 12th, that is x to the 5 plus 12, which is x to the 17. So just because we add numbers in the beginning doesn't change anything. X to the negative 3 times y cubed. Well, the only thing that has a negative exponent is this x. So what we're going to do is drop That x to the denominator, x to the negative 3 is 1 over x cubed. And now this is fraction multiplication. This is just like y cubed over 1. So 1 times y cubed over x cubed times 1, y cubed over x cubed. Which, now that we have established how that works, what you can also do going forward for all different problems is if you have multiple terms like this, you can just drop that x cubed down knowing that all of it is together. So don't feel like you need to show this middle step of doing 1 over x cubed times y cubed because we had multiplication in the beginning. This is all one term, so we can treat it all as one term and not need to do things in the middle. But whatever's easier for you, do it that way. X times y to the negative 1. Okay, well, everything in here is multiplied together, so we can distribute the negative 1. Well, x to the negative 1, y to the negative 1, drop those negative exponents down and make them positive. 1 over x to the 1 times 1 over y to the 1, that is fraction multiplication. 1 times 1 is 1, x to the 1 is x, y to the 1 is y, x times y is xy. But also, you can also just look at this and say, this whole thing is being raised to the negative 1. We can just drop the whole thing down. Simple as that. There's nothing wrong with that. 5 times xy squared. Again, the only thing being raised to the second power is x times y. X times y is multiplication. We are allowed to distribute the 2. And we just get 5x squared y squared. That's it. Nothing else that needs to change. But if we include that 5, well, this is now 5 times x times y. Well, all three of these things are being multiplied together. So when we distribute the 2, all three things get that 2. The only difference is x squared, y squared, we can't do anything with, but 5 squared we know is 25. 5 on the outside, xy cubed. Again, the only thing getting the cubed is going to be x and y. But if we include that 5 in there, now everything gets the cubed. 5 cubed is 125. Well, let's start making some things negative. Let's see how it changes. Here, same thing. Only thing being raised to the second power is x times y. Well, negative 5 just sits on the outside. But the second that we include negative 5 on the inside, now all three things get that squared. But don't forget, this whole thing gets the squared. So this is negative 5 squared. Negative number raised to an even power is positive. Negative 5, xy cubed. All right, distribute that 3. Nothing else to do there. But the second that negative is on the inside, now we have negative 5 cubed. Negative 5 cubed is negative 125. Again, placements of negative numbers, very, very, very important. X times y squared over x to the 5th, all raised to the 5th power. Okay, everything on the inside, x times y squared divided by x to the 5th. Everything is being multiplied or divided, so we are allowed to distribute that exponent. All of these are powers to a power, so of course the x just picks up the 5, but y squared will be multiplied by 5, and x to the 5th, the exponent will be multiplied by 5. 2 times 5 is 10, 5 times 5 is 25, and notice we have 5x's up here, 25x's down here. We can cancel out 5 of them. If you also want to use the rules of division, you can do that too. You would have x to the 5th minus 25, 5 minus 25 is negative 20, and that x to the negative 20 would come down. Similarly, this is a pretty okay way of doing it, but you could have had some foresight to say, oh, look, we have multiple x's on the inside already. We have 1x here, we have 5 down here. Why don't we just cancel out that 1x to begin with? Cancel out one of the x's, we're left with 4 of them. Now we can distribute the 5 via exponential multiplication, and we can get the same answer that way. So what you're going to see is a lot in this class, a lot of different paths to get the same answer. Negative 2 times x to the negative 2, y to the negative 2 to the negative 6. The only thing being raised to the negative 6 power is x to the negative 2, y to the negative 2. So what you might want to do is say negative exponent, drop it down. and then you'll have a -6, and then you have to flip it again. There's no right way of doing it for every problem. Some problems you might want to do, flipping these negative exponents and then flipping it again with this -1. But a pretty good way of going about these problems is to just distribute that -6 via multiplication and then flip stuff later. But if you're comfortable flipping first and then multiplying exponents, you can do that too. Like I said, not one way of going about this. Alrighty, well, x to the -2 times -6, that's 12. So -2x to the 12, y to the 12. So notice we had so many negatives in the beginning, but just because we had so many negatives in the beginning doesn't mean that we will necessarily all have negatives at the end. -2x over 5, all raised to the -4. We have a fraction with a negative exponent. Negative exponent we can get rid of by flipping the inside. 5 divided by -2 times x. Everything is multiplied or divided. Everything can get a 4. So we can simplify that way. So lots of rules of exponents being used. Okay, and we're going to finish up P2 with scientific notation. This is not a really long part, but many of you that are watching this might be STEM majors, you might be bio majors, chem majors, and you'll notice that you use very big numbers sometimes, or sometimes very, very small numbers. For example, this is, let's see, million, billion, trillion, quadrillion, quintillion. This is 37 sextillion, 600 quintillion. That's a lot of atoms. But is it efficient to write 37 sextillion, 600 quintillion over and over again? Or is there an easier way? And that's where scientific notation comes in. Scientific notation are numbers that are written in the form a constant times 10 to some power. So with so many decimal places, instead of writing all of those zeros over and over again, what we can do is simplify all those decimal places, or all those like hundreds, tens, hundreds, thousands, and so on. We can simplify that with 10 to the n. So c is going to be some constant, n is going to be some integer. It could be a positive integer, it could be a negative integer, it could be 0. So one restriction that we have is that this c must be between 1 and 10. So we need a way to say, okay, when do we stop moving decimal places over? When do we stop having zeros as places? Well, what we're going to do is make sure that this constant is always between 1 and 10. It'll make a little bit more sense when we do an example. If our number is very big, for example, 37 sextillion, 600 quintillion, that number is very large. In the case where your number is very large, this n, this power, should be positive. And if the number is very small, right, this should also mean that n is negative. Okay, well, think about this. If we have 10 raised to some positive power, let's say 10 to the 10th power, well, 10 to the 10th power is really, really big, right? 10, 100, 1,000, 10,000, 100,000, million, 10 million, 100 million, billion, 10 billion. I think I got that right. Well, if we're multiplying by something times 10 to the 10th power, that's a really big number. So if n is positive, the number is large. If the number's negative, it's very small. Think about it this way. If we multiply by times 10 to the -10, 10 to the -10 is 1 over 10 to the 10. So we're, in a sense, dividing by, 10 billion. So if we're dividing by 10 billion, our number should be very small. So what we're going to do is take whatever our number is and move decimal places to the left or to the right to determine the magnitude of n. So last slide, let's convert some to scientific notation. So let's convert 37 sextillion, 600 quintillion into scientific notation. So what we're going to do is, we know that we have an imaginary decimal place right here, and we're going to move it over so many units until we get a number that is between 1 and 10. So we move over 1 decimal place, and then we move over 2 decimal places, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And again, don't forget that we want to get to a point where the number is between 1 and 10. If the decimal place is sitting right here, well, everything to the left of the decimal place is 37,600,000. That's definitely not between 1 and 10. So we want to stop when, if we dropped our decimal place right there, it's between 1 and 10. So let's keep going. 16, 17, 18, 19, 20. If we stop the decimal place right here, everything to the left is 376. That is not between 1 and 10. Okay, let's go 21 decimal places. Well, if we drop the decimal place right here, we'd have 37.6, not between 1 and 10. But if we go one more decimal place, 22 decimal places in total, if we drop the decimal place right here, notice this would be 3.76. And 3.76 is between 1 and 10. Now, we want to write some power of 10 here. We moved over 22 decimal places, and this number is very big. If the number is big and we moved over 22 decimal places, this should be positive 22. All right, let's do a slightly smaller example. Let's do 5,001. So there's an imaginary decimal place right here, and let's move over until we get a number between 1 and 10. We move over 1, that's 500.1, not between 1 and 10. Move over here, 50.01, not between 1 and 10. Move over here, 5.001, and that's between 1 and 10. Well, so we're going to be 5.001. How many decimal places did we move? 1, 2, 3, 3 decimal places. Okay, so since the number is big, 5,001 is big, that 3 should be positive. One more example like this. Let's stop when we get a number between 1 and 10. So let's move over 1, 2, 3, 4, 5, 6. If we drop the decimal place right here, we'd have 4.123. That's between 1 and 10. So 4.123 times 10 to the positive 6. We moved over 6 decimal places. This number is big. 4.123 times 10 to the 6. Okay, well, let's deal with a small number now. Let's see how this changes. Well, instead of moving decimal places to the left, let's now move decimal places to the right. Well, we don't need to worry about where that decimal place is anymore because it's sitting right there. Okay, so let's move it over until we get a number between 1 and 10. Let's move it over 1. This would be 0.996, not quite, but move over one more spot. This would be 9.96. Okay, we've moved over 2 decimal places, so we know it's either going to be to the power of 2 or to the power of negative 2. 0.0996 is small, so if it's small, this will be negative 2. All right, let's do the same thing. 1, 2, 3, 4, 5. We'll stop right here, so that would be 2.6501. And we moved over 5 decimal places. Well, this number is small. If the number is small, it is going to be negative 5. Okay, we can also convert to standard notation. So if we are given scientific notation, we can go backwards. All we're going to do is move the decimal place in the correct direction. So we know we need to move 6 decimal places, but how do we know which direction we need to move? Well, this is 10 to the positive 6. So we know our number should get bigger. If we move to the left, our number is going to keep getting smaller. So we definitely don't want to move to the left. For positive, let's move to the right, which is kind of a nice way of thinking, right? Real number line, positive is to the right, negative is to the left. So in this case, positive exponent, let's move it to the right. So let's move 1, 2, 3. And you'll notice that we don't have any more places to move. So instead of trying to keep moving, if we moved 3 decimal places over, we have nowhere else to go. Well, we need to move 6. We moved 3. We need to move 6. Let's add 3 zeros at the end. And now it might be a little clearer to see. If the decimal place was originally here and we move it over 6, 1, 2, 3, 4, 5, 6. So go until you can't go anymore, and then fill up the extra spots you were supposed to move with zeros. 9.872 times 10 to the negative 8. Well, negative left. Let's move the decimal place over to the left. Well, we move it over 1, and we don't have anywhere else to go. So we need to move over 7 more decimal places. Well, instead of actually moving 7 more, why don't we just tack on 7 zeros? 1, 2, 3, 4, 5, 6, 7. 5.1 times 10 to the 0? Well, 10 to the 0 is just 1. Any number raised to the 0 power is 1. 5.1 times 1 is just 5.1. Let's convert 3.99 to scientific notation. All right, well, we don't need to move the decimal place over at all. It's already between 1 and 10. So 3.99 is 3.99 times 1. And 1 is 10 to the 0. So if the number doesn't need to be changed at all, it would be times 10 to the 0 in scientific notation, but we don't typically do this. So, but still, good practice. Okay, that's the end of P2. In P3, we start to look at some polynomials. So I will see you in P3. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska-Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.